I'm Carl Yukich, and this is Lab 3. So our instruction for this lab is that the purpose is for part 1 is to find the mass of a black hole based off a randomized seed from an input email address. This model will then simulate the orbit of a star against a stationary black hole, and we're to find the mass of that black hole. Part 2 uses a different computational model where we find the initial velocity of a spaceship escaping a planet's gravitational pull so that it flies around a black hole with the mass from part 1 without crashing into the planet or the black hole. Principles covered are the momentum principle, Newton's second law, and gravitational force, and the main results are listed. So our key concepts for this are Newton's second law: objects in motion will stay in motion unless acted upon. This could be described as F equals ma, or the change of momentum is equal to the force times time. We also have universal gravitation, where the force due to gravity is equal to the negative gravitational constant times mass 1 times mass 2 divided by the distance between those two objects squared and their direction. It's negative just due to the nature of gravity, where forces attract, and gravity G is our gravitational constant. It's a non-constant force, and this is not to be confused with the force of gravity at Earth's surface. We also have parallel and perpendicular forces, where F net is equal to change in momentum over change in time, which is the momentum principle, and it can be split into perpendicular and parallel axis, where P hat is the parallel and N hat is the perpendicular. And this is true as long as the system is moving with curvature. P hat is in the direction of the momentum, where F net parallel is equal to change in momentum over change in time times the direction of the momentum. And N hat is the direction in the spin of the object, and perpendicular P hat, where F net perp is mass times velocity squared over r, and the direction of that spin. So for part 1, we have our initial conditions with our gravity component, or gravity constant, star mass, and our time. Then we go down here and we're defining our momentum, which is just P initial is mass times velocity, mass times velocity. Down here, we're defining our deltas, which is just our delta V, which is final minus initial, delta P, final minus initial. We define dBTD by defining the change in time, the change in momentum over the change in time, stick that into a force. And then we define our parallel component, we find the direction vector, we find the magnitude of our change of momentum, and then we multiply the magnitude times the direction to get our change momentum, and we stick that into a force of parallel. Then we can calculate the perpendicular component by subtracting the whole component minus the parallel component to get our change in perpendicular momentum, and we can stick that into a force. And then we calculate our black hole mass by rearranging that gravity equation from slide 2, and then we can print and run it. These are the results listed, and here is the simulation. So for part 2, we have our code. We have our initial conditions set up here with our black hole mass from part 1, same gravitational constant, same planet mass. We now have a ship, which is 70 to the 10 mass. And our time, we have our T max, which is just 1 hour down here. And here are our results we found by plugging in different random values and just trying to see what worked in the simulation. This calculation loop is just rearrangements of this gravity equation, where we have to find forces on the planet and the spaceship, since they're the only things moving, and we have to take into account the black hole and the planet, or the black hole and the ship for the planet. So we find our distance from the black hole to the planet, and then we put in the force from the black hole on the planet. Do the same thing for the ship. We have to find the distance from the ship to the planet and the force of the ship on the planet, just using these equations. Put that as a total F net for the forces on the planet, and do the same thing for the ship, just different rearrangements of variables. And then to make things move, we just stick everything into a momentum equation where we calculate the velocity and then calculate the position based on that changing velocity. And here is the simulation. This is at double speed since the simulation moves slowly, but we can see the ship shoots out and curves around the black hole without hitting it and is able to escape the atmosphere of the planet. What does it mean? So how are the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? So mathematically, this is the same thing, as force can be defined as the change of momentum over time. It's just that the direction of the F net, perpendicular and parallel, are very easily observable, but are much harder to calculate the magnitude of due to the amount of different forces that can be acting on an object, versus change of momentum can be measured and observed very easily, as the only thing you need for momentum are mass, velocity, and change in time. What initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? So our velocity needs to be more diagonal upwards towards the black hole, and having enough vertical velocity to be swinging around the black hole, as well as not going too fast X direction to go and shoot past the black hole's gravitational pull. And you can see the model here with these results plugged in. We have a lower X speed and a higher Y speed, and this is able to have the ship go in a sort of circular orbit.